Hello everybody, my name is Ashley Russell, and today I'll be talking about the London Department assignment, and this is for Project 2 in ENGI 340. So let's start with a problem description. The original OPL problem was called decentralization, and so basically the problem states that a large company in London wants to relocate some of its departments. The departments can move either to Bristol or Brighton, or they can stay in London. There are benefits to relocating, such as less taxes and cheaper housing, but the communications costs would be higher if you relocated to a different city. And then one of the constraints was one city can house no more than 3 departments, and the goal is to assign the departments in such a way as to maximize the total benefits. So I first started this problem by modeling it in Excel. It's easier for me to work in Excel first and then switch to code. So I set it up in Excel like this as an assignment problem. So I chose this problem because as I was thinking through it, I realized that once an assignment is made and every department is assigned to a city, there are going to be a bunch of cost constraints that aren't actually used. And I looked in the code, and the original code had a bunch of constraints that just are useless, that aren't ever used, and just end up making the code run for longer. So I saw that as an opportunity to improve and to make some changes. And then I also saw it as an opportunity to model it in the way that we learned in class, which is different than how the problem was originally modeled. And then also, the problem is set in London, and that's a city I hope to visit someday, so that just made it a little more fun. So to compare the models as is and to be, the as is, the original problem was solved using 0 to 1 integer programming, which just uses Boolean variables to make assignments, and it had many unneeded constraints because the code set up loops that ran through every possible scenario, but that was just kind of unnecessary. So I plan on solving the problem using the technique we learned in class, where I'm going to assign names to all the variables and actually write out the objective function and the constraints, and then I'm going to remove unnecessary constraints to make the problem solve faster. So this was a difficult part of the problem, trying to make a mathematical model for the original problem, but I was able to do it, and I just broke it up in the different sections here. So this first constraint is each department has to be assigned to only one city. And then the second one represents how each city can contain no more than 3 departments. And then the following 3 constraints are for calculating communication costs and quantities between departments and cities. And then finally, the objective function, where B is a benefit of relocating, C is the quantity of communication between departments, and D is a cost per unit of communication between the cities. So in their model, as I said before, they used a loop to make calculations for every single possible combination of department assignments and associated costs. So there ended up being 162 total constraints and 69 decision variables. But like I said before, if you look at the original problem, once assignments are made, only a few of these constraints are actually needed. So this causes the code to run for a long time unnecessarily. And so in my model, I only include the relevant constraints. And then in their model, they left out a few values of costs and quantities, so I just added those into mine. And so my mathematical model has the objective function actually written out like this, and subject to the constraints as follows. So each city can have no more than 3 departments, and each department can only be assigned once. And then just to kind of help you understand how I was naming these variables, A sub ABS means Department A is assigned to Bristol. And then on the bottom, the second example, A sub BR is Department A is assigned to Brighton. So I used that same idea for all of my variable names. And so this is where I really made a lot of changes to the code. So these are the constraints that are used to calculate the communication costs between cities once the departments are assigned to a city. And we only need 6 of them. The original problem, they had a million of these that weren't even being used. Once the assignment is made, you only need these 6. So just to give an example of what this means, Department A is assigned to Bristol and Department C is assigned to Brighton. And you calculate the costs of the communications using this formula, meaning the cost of communicating between Bristol and Brighton times the Department A located in Bristol times Department C located in Brighton times the quantity of communication between Departments A and C. And so that's how I wrote each of the constraints for calculating communication costs. So let's move over into the code. So here is the code for the first part of my problem. I broke it into two pieces. So the first part is just the code needed for the assignment, and then the second part, the second model, is for calculating the costs. But let's just focus on this one for now. So these are the variables for the benefit of relocating. So just to go over quickly again, BABS is equivalent to the benefit of Department A moving to Bristol, and BABR is a benefit of Department A moving to Brighton. Here are the variables representing all the ways departments could be assigned to the cities, and so these had to be the same. I couldn't remove any of these. These are all necessary for the assignment. And then here we initialize what we're trying to maximize in our function. So we say maximize total benefit subject to, again, these constraints, I just rewrote them down here just for reference. And then here are these constraints. These are important. So one city can have no more than 3 departments, and each department must be assigned to only one city. And then the objective function. So I hard-coded these numbers in here so that when we run this, this area down here is clean and there's not too much to sort through. So let's go ahead and run this and see what we get. It might take a few seconds. Okay, so in order to keep all this clean and not have just a bunch of variables over here where it's hard to sort through and find the information you want, I just left these in a comment and hard-coded them in down here, so this would be very easy to see over here what the assignments are. So here our total benefit is, this is in thousands, so $80,000 is our total benefit, and everywhere we have a 1 is where a department is assigned. So here this means Department E is assigned to Brighton, Department C is assigned to Brighton, Department B is assigned to Brighton, and Department D is assigned to Bristol, and Department A is assigned to Bristol. So these are assignments, and when I modeled this in Excel, Solver gave me the same results, so I feel confident that this is accurate. Okay, so now let's go over to the costs model. So I just put these in here just as a reference. So these are the variables representing the relevant quantity of information moving between departments. So these are the only relevant departments once assignments are made. And same with here, these are the only relevant costs per unit of communication. In the original model, there were a bunch of these, and really all we need is these ones I have here. So we're trying to maximize our total benefit overall. So again, these are just the departments that have been assigned, and these are the constraints for the quantity of communication between departments, and these are constraints for the cost per unit of communication between the cities. So we know our total benefit is $80,000 from here, and then this is the communication costs. And okay, so what this means right here is this is referring to Department A being assigned to Bristol and Department D being assigned to Bristol. So these two departments, both in Bristol, have a communications cost associated with them. So we have to look at the cost per unit of communication between Bristol, so Bristol to Bristol, and that, which is 5, which is where this number comes from here, and then the quantity of communication between Department A and D, which is 1,500, which goes here. And so I just did that same process over and over again for all of the departments and all the assignments. And then, of course, the total is our total benefit, which is 80,000 minus whatever our communication costs are. So let's run this. and see what we get. Okay, so our total benefit we know is 80,000. Our communications costs are 65,100, and so our total benefit is $14,900. And this is actually the same answer that the original problem gets. So we can just run that really quick just to verify and see that it is the same. This one will take a little bit longer. Okay. So they have their answer down here. So their benefit is 80,000 and their costs is 65,100, which is the same as what I got in my model. So let's head back to our PowerPoint really quick. So just to compare the results, the original problem, the total benefit was 80,000. The total communications costs were 65,100, and the total revenue per year was $14,900. And that's the same that I got in with my model, my method. They used 69 decision variables, and my model was able to cut that back to 47 decision variables. So I reduced the number of decision variables by 32%. And then I ran it several times, and the average run time for the original problem was 0.46 seconds, and with my method, the total average run time was 0.25 seconds. So that's a reduction of 46% in runtime. And so in a problem this small, you can't really tell the difference. You don't really notice, but if this problem were bigger and had a lot more going on, reducing the runtime by 46% could make a big difference. So I'm glad you took the time to listen to my video. Please check out the rest of the YouTube channel, and thank you for listening.